Hello, everyone. This is the lecture for section 8.1, non-right triangles, the law of sines. So in this section, in chapter 8, um, we're going to be dealing with non-right triangles. So in a right triangle, we are guaranteed one of the angles to be 90 degrees, right? Uh, This section covers everything that doesn't have a 90 degree in it. It has it. None of the angles are 90 degrees. Okay, which means we might have uh, oblique triangles. Okay, which means one of the angles is bigger than 100 and sorry 90 degrees. Right. So uh, that's what we're going to cover in chapter 8. Right. To start, we're going to do just the law of sines. Okay. And basically, 8.1 is just a different way to solve out the different lengths of oblique or obtuse triangles, basically. Okay. The first thing I need to cover is some geometry. Okay. In particular, the angles in a triangle and in a straight line. Hopefully, you guys remember this from geometry at least, right? Basically saying that if I have an alpha, and actually let me use a nicer, more brighter color on the orange, okay? If I have an alpha, a beta, and gamma for the angles inside of a triangle, right? All of these have to add up to 180 degrees, okay? That is the equivalent of all the angles, right? If you add them all the way up over 180 degrees across sort of a flat line, right? All of them have got to be, they have to add up to 180 degrees. Okay. I've got some practice problems for you guys to do. Okay. We'll do those in class. One more thing that I need to pick up, that we need to pick up in order to do any of the trig that we're about to do, any of the law of sines that we're about to do, is to cover some of the triangle congruence theorems and the idea of whatever a congruence means. Okay, so first of all, let me go ahead and cover a definition. Two angles are said to be congruent, so essentially the same, right? If they share the same shape and size. And that is talking about all the angles and all the sides, both together. Okay? Which brings up a theorem. Okay? These are what are called the triangle congruence theorems. These are the ones that you remember maybe from geometry that had all of these. So SSS, SAS, ASA, AAS. Okay? Uh, if you have two triangles that match any one of these four, okay, then they are said to be congruent. There's no possible way that that two triangles that fit any four of these are going to be different. Okay, and the idea behind these is that you have to sort of do them in order. Okay, you can't sort of skip a part of the triangle. So, for example, right, let me do the first one. If you have side, 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 if you have this side is equal to this side is equal to this side, and this side is equal to this side, right? There's no possible way that the triangles are going to be different, okay? And this now matches up the angles as well, right? Right? Okay? Let me do another one, okay? Suppose I had side, angle, side. So side, angle, side, okay? And that's the same as side, angle, side, right? Then that means this missing side on both of the triangles, there's no possible way they can't be the same. Okay? Hopefully you guys sort of remember how this works, right? Last one, angle, side, angle. Okay, so for example, angle, side, angle. Angle, side, angle. There's no possible way that this third angle is not uniquely determined already, right? And there's no possible way that because of these two angles down here, this one and this one, right? There's no possible way that these lengths are going to be any different. There's no way we can draw them, right? Without these being the same, right? Okay, let me do the very last one, the angle, side. Okay, so angle, side. So angle, and actually this should have two little, there we go, two, side. There we go. Okay. So if these two angles are the same, if this angle, I'm actually going to highlight in pink this time, if these two angles are the same, right, and this side is the same, right, it is very difficult to draw this angle and this angle differently. Actually, it's not possible at all, right? And that uniquely determines this side, this one down here. Okay? So this is what it means to be congruent. These are the four big ones, at least, that you should remember from geometry. I'm just going to cover them here. There's no, I'm not going to require you to prove them, okay? Just know that these exist. And what we're going to do now is we're going to start playing around with the law of sines in particular. So the diagram for it is super easy to remember, okay? So I want everybody to look at this. You have sides A, B, and C, right? The opposing sides, sorry, the opposing angle is going to be the Greek letter. You guys hopefully see that, right? So B goes to beta, A goes to alpha, C goes to gamma, okay? And the law of sines is this right here. Basically, if you take the ratio of any angle and its opposing sides, right, they've got to be equal. Okay, I know that this is a brand new thing for a lot of people to sort of look at, right? Why do we have two equal signs in between? This is not an equation anymore, right? The idea is you can choose the two that you really need. So for example, I can do sort of sine alpha over A is equal to sine gamma over C, right? Or I can do sine beta over B is equal to sine alpha over A. It really depends on which one you want to use, okay? This equation is also on your yellow sheet, okay? You don't have to memorize it. Please don't memorize it. You have the yellow sheet in front of you, right? But if you do need to construct it, right? If you do need to construct the triangle, that's, I think, the best way to remember it, right? You have your sides, right? And then the opposing angles inside the triangle, those are going to be your Greek letters. And then you just fit it in to the equation that's right here. Ah, wanted yellow. There we go. Okay. Okay. So let's try this out. Okay. Oh, not yet. Not yet. Not yet. Okay. So there's a reason why I had to show everybody those trig congruence theorems. Okay. There does seem to be a problem sometimes, and this is what we call, when we study law of sines, we call it what's called the ambiguous case. Okay. This one's the ambiguous case. Okay. So if you look at our triangle congruence theorems, right? If you do any one of the triangle congruences that are there, right, you're going to get one unique solution. Okay. There is what's called an ambiguous case, and notice how I'm not going to say it. Okay. This how would I say it? A triangle, right, that matches this congruence here, right, may not be the same, even though an angle, a side, and a side, right, are equal to each other. Okay. There are three different possibilities. Okay. And that's what I'm going to cover down below. Okay. The first one, where the sides produce only one triangle, and this is going to be a right triangle in this case. So, for example, right, I have an angle, and I'm gonna kind of do this. I don't know this side. I'm just gonna, right, but I do know that it's got an angle, that one, right, a side and a side. Okay, if this length is just right, then what we have is a right triangle, basically. Okay, this is the one that is one solution. We only have one solution in this case, right? Because that second side drops down just perfectly to meet up with this angle right here, this angle right here. Got it? Okay. Next one is two solutions. So I'm going to do the exact same thing. I'm going to make a nice long line, right? And I'm going to do two triangles here. One of them is going to be do it this way. Let me undo that. There we go. You know what? I'm trying to draw this nice enough to explain it, and I'm failing all over the place. There we go. Okay. Now let me move it up a little bit. There we go. Okay. I'm going to draw a line, right? Okay. Notice that I drew my line a bit too far. I'm actually going to shorten it a little bit. There we go. Okay. Too long still. There we go. Okay. So remember, right? Angle, side, side. Okay. Here's where my two solutions come in. Okay. I'm going to put down two triangles, right? And I should do it in a different color. I'm going to do it in purple. Okay. One triangle is going to be like this. So basically, I get to grab this end and sort of fling it inward to here. Okay? This purple triangle is one triangle. Got it? I'm going to draw another one now. Okay? But this time I'm going to do, I'm basically grabbing this and flinging it out this way. Right? So I have now this triangle. I have just drawn two triangles, right? I have just drawn two triangles where an angle, a side, and a side are equal, but they are two different triangles, okay? In which case, right, if you take a look at this angle down here and this angle right here, okay, one of them is going to be bigger than 90 degrees, and the other one's going to be less than 90 degrees. This triangle has two solutions. Okay, so we have to check our law of sines when that happens in order for us to see whether or not this is valid or not. Okay? Okay. And then the last one, so that was B. C is the one where it's no solution. So basically saying this. Okay? I'm going to draw my line again. Okay? And I'm going to draw my triangle. Angle. Side. Side. And I'm going to terminate my triangle right there. Okay? Okay. What happens in this one, right, is basically this. This angle is way too big for this length. Does that make sense? So it doesn't even make a triangle, right? When this happens, right, you'll notice it. I'm going to do an example, right? But what essentially happens is the computations just don't work out. You'll get a DNE, okay? But this is essentially what happens when you have no solution under the law of sines. That basically you drew a triangle, you tried to draw a triangle, right? With one side that wasn't going to match a triangle at all anyway. Got it? Okay. So let me go ahead and start doing some of the examples here. Okay, so the first one, find the missing lengths of the triangle using side angle to the nearest tenth. Okay, so notice what we've got here. This one's 50, this one's 30. This last one up here is going to have to be 100 degrees. Okay? Okay. At this point, everything's already sort of set up for us. We get to just plug stuff in, right? So then let's go ahead and find B first. Okay? In order to find B, okay, sine of 100 degrees all over B is equal to, right? I'm going to use the 50 because hopefully you guys see this. The angle and the side are provided here, right? For both. Sine of 50 degrees over 10. So then that means my B has got to be 10 times sine of 100 all over sine of 50 degrees. And this is degrees. Woo. Okay. Please make sure that when you are computing these out on your calculator, there's no way you're going to be able to do this without a calculator now, that your calculator is set to degrees. Make sure it is set to degrees. So then that means if I actually plug this into a calculator, I get 12.855. That is going to be our B. So bam, bam. Okay? So this is going to be 12.855. Okay, next one. Let's say I wanted to find C, this one over here, right? Sine of 30 degrees over C has got to be equal to, I'm going to use the one that we were using just now, sine of 50 degrees all over 10. Yep. C, if you solve this out, 10 sine 30 degrees all over 50. Oh, sine of 50 degrees. Whoopsies. Compute this out right. 6.5270. Boom. Okay. So that means this right here, 6.5270. There we go. We have completed all the measurements for this triangle. Okay. Okay. So this is just getting us used to how to use the law of sines to compute the missing stuff for any triangle, whether it be an angle or a side, right? Okay. Now let's go into whether or not you're going to have one solution, two solutions, or no solutions. Okay? So let's go ahead and I'm going to demonstrate the one solution. Okay? Notice how I have this set up over here. I have an angle, side, side. Okay? Which is the word backwards, right? Okay. All right, so let's say I wanted to find side A. Okay, so I'm going to go ahead and start labeling stuff. Please, please, please label stuff, right? So if this is A, this is going to be my alpha. In our case, since it's not really, stated, I'm going to make that beta, which makes this equal to my side B. And this is going to be my side C, which makes this end right here gamma. This angle right there, gamma. Okay. So for this one, what we're going to do is we're going to try to find our angle gamma first, okay? So we see that we have beta and B, so then that means sine of my angle beta, 85 degrees, divided by 12 has got to be equal to sine of gamma divided by 9. This simplifies down to this. I'm going to get sine of gamma is equal to 9 sine 85 degrees divided by 12. If you compute this out, this 9 sine 85 divided by 12, you get, make sure I'm in the right mode, 0.7471, okay? Which means, what am I doing? Gamma, the angle gamma is equal to sine inverse of 0.7471, and that is going to be 48.34 degrees, okay? Now, I do want to go back to this statement right here, okay? There are actually two angles, right? So sine of gamma is equal to 0.7471, right? When H-E-N, gamma is equal to, there are two angles that do this, okay? The first one we just computed from up above using our sine inverse, 48.34 degrees. The other one that does it, okay, and you guys can verify, is this, 131.66 degrees. So if you grab sine of either one of these two angles right here, that'll get you this right here, okay? Which means both of these angles, hopefully you guys are following along here, both of these angles will satisfy our initial statement, okay? This is how we double check to make sure that we don't have what's called the ambiguous case, the one from below, the 2 solution, okay? So here's the verification, okay? All of the angles in, let me write it down, huh? To 180 degrees. All the angles inside the triangle have to add up to 180 degrees, right? So we know one of them is 85 degrees, right? So if we do 85, right? Actually, let me do it this way. 180 degrees, right? Minus 85, that's already there, right? Minus 48.34. Let me compute it really quick. I thought I had this one. 180 minus 85 minus 48.34. This is 46.66 degrees. Okay? Now, hopefully you guys see, right, that this is actually valid. This is okay. Okay? So then this means that my triangle is going to have an 85-degree angle, right? A 48, I'm going to do it this way, plus 48.34 degrees plus 46.66 degrees, right? If we add all these together, we get 180 degrees. This is a valid triangle, no problem, right? But now let's try the other one. So 180 degrees One of them is already reserved. It's got to be 85 degrees because that's already in a triangle, right? Minus 131.66 degrees. Okay, and if we do that, let me actually do this one. 31.66. We get negative 36.66 degrees. This is a heck no right here, right? This cannot happen. Way too thick of a marker. There we go. A-P-P-E-N. This cannot happen, okay? So even though two angles are produced in this case, right? One of them does not work. This one does not work, okay? So in this case, what we just did, right, was we found our missing angle. Okay, we found at least gamma up here, right? From here, we're supposed to be able to find the rest of the missing lengths. I'm going to leave the rest for you all to do, okay? But it's just as simple as how I showed from the very first example, okay? Okay, what I do want to go to now is the two solution one, okay? So this one, right, hopefully you guys will see that there is going to be, and let me scroll this over a little bit, there's going to be two triangles. There's going to be this triangle, right? Let me actually thicken that up again. There's going to be this triangle, bam, bam, bam. And then there's going to be this triangle. I'm going to do it in a thick purple this time. Bam, bam, bam. Okay. Both of these triangles have the same angle, one side and another side, right? But the shapes of the triangles themselves are different. Okay. This is what's considered the ambiguous case. Okay. So we're going to try to do this all over again. Okay. Again, label what you need to, right? I'm going to make this alpha, so then that means my 6 is A. This is going to be beta, so that makes this B. And this angle way over here is going to be gamma, which makes this last side C. Okay? All right. Hopefully you guys see that we have alpha and A. Okay? So let's go ahead and try to solve for this angle B, because that's going to be, as you guys saw just now, this is going to be my ambiguous angle that might be two angles that we need to deal with. Okay? So find my angle beta. Okay? Start off how I usually do, right? So sine of 35 degrees all over 6 has got to be equal to sine of beta all over 8. Got it? You guys see how it just fits into the equation, right? Okay. So now I'm going to get this, right? I'm going to solve this out. I'm going to get sine of beta is equal to 8 sine 35 degrees all over 6. If you throw this into, yeah, and I didn't compute it again. I thought I had these numbers ready. 8 sine 35 degrees divided by 6. I get this value right here, 0.764, whoops, 76476. My angle beta is going to be sine inverse of 8 sine 35 degrees all over 6, okay? Which means it's going to be the sine inverse of that 0.764 blah, 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 right? Sine inverse, whoops, of that mess right there. I get this angle right here, 49.886 degrees. Got it? Okay, again, right? I want to go back and analyze this statement. Sine of beta is equal to 0.76476 when beta is equal to two different angles. We found one of them, 49.886, right? Or the other one is going to be, let me compute that. I thought I had it. 49. 130 degrees, 130.114. Okay? So that means my triangle for this angle right here, for that beta angle, has two different values. We have to check both. Okay? So again, right? All the angles in a triangle should add up to 180, right? So I'm going to do this. 180 degrees minus the reserved 35 degrees that we have for one of these angles already, right? Minus 35 minus 49.886 minus 35. This gets us a 95.114 degrees. So then this means, right, 35 degrees plus 49.886 degrees plus 95.114 degrees, right? This right here is equal to 180 degrees. This right here is a valid triangle. Okay? Let's check the other one. Okay? 180 minus 35 minus 130.114. 180 minus 35 minus 130.114. This is equal to 14.886 degrees. So, watch this, right? 35 degrees plus 130 degrees, 130.114 degrees plus 14.886 degrees. This is equal to, that's degrees, 180 degrees. This is also a valid triangle. Okay? Let me do this. Hopefully everybody's been able to follow along up to here. That's supposed to be 35 before I erase it. There we go. Okay. I'm going to do two triangles. There's going to be this one. Okay. And then there's going to be this one. Okay. And I'm actually going to do them in the colors that I just highlighted them in, okay? So the first one is going to be, actually, let me do this one. Okay, where we have these measurements, right? This one is 35. This one is 130.114 degrees. And then this one up here is going to be, I'm going to write it down right, 14.886. Okay, this is on top of this side being 8 and this side being 6. Okay, this is a valid triangle for us to solve out. Okay, let me draw the other one now. Okay, where this angle right here, 35 degrees, okay, this angle is going to be my, what is that, 49.886 degrees. And this angle right here is my missing 95.114 degrees. This is also, again, assuming that this is 8 and this is 6. Here are our two triangles, right, that really muck stuff up. Okay? Okay. I'm not going to compute the rest of this because at this point, I'm pretty sure everybody can sort of work out the law of sines, right? But I do need to point out the ambiguous case, basically having these two triangles down here. Okay? You have to check for both. You have to check for both. Okay? And the way that you check it is this. This is always going to be the check. Okay? And the root for that check is going to be this thing right here. That to that. Okay? Okay. Last case that I need to cover. No solution. Okay? So this is going to look a little weird. Okay? But we're gonna try it. We're gonna see how far we can get. Okay? Find all possible triangles with a side of length 4 opposite of an angle 50, right? And a second side length of length 10. Okay, make my triangle. Bam, bam, bam. Okay. Let's make this my 50-degree angle. 4, and it doesn't matter which one I call it because it just says the second side length, right? I'm going to make this one 10. Okay. I'm going to start labeling stuff. So this is going to be my alpha. I'm going to make that beta. I'm going to make this gamma. So that means this side's going to be C. And this side's going to be B. And this side's going to be A. Okay. We are off to the races. Okay. We have beta and B. So sine of 50 degrees over 4 is equal to, at this point, let's take a sine of alpha and A because that's at least the one that's missing one thing, right? So then that's going to be equal to sine of alpha divided by 10. So I have this. Sine of alpha is equal to 10 sine of 50 degrees all over 4. Okay? If you throw this into your calculator, 10 sine 50 divided by 4, you get 1.91511, right? Okay. Alpha has got to be equal to sine inverse of 10 sine 50 degrees all over 4, which is the same thing as sine inverse of 1.91511. Okay. Hopefully you guys see this should trigger does not exist. Okay. You're asking, right? Let's go back to this statement right here. You're asking sine of some angle theta, or sine of some angle alpha to be bigger than 1. You're asking the sine of an angle to be bigger than 1. We know that sine bounces between positive 1 and negative 1. So for it to be bigger than 1 can't happen, right? This is the no solution case. This one's the no solution case. Since the computation presents a does not exist. Okay? So this is the way that you find the ones that are no solution. Okay? Okay. Moving right along. Area of a triangle. Okay. We know that the area of a triangle for a good old right triangle, right, is 1/2 times base times the height, right? But that always assumes that the height makes a right angle with its base, okay? This is the actual equation of the area of a triangle, of a rando triangle. Let's suppose that you had an oblique triangle, okay? This is the equation for the area. Okay, so I mean, I'm not gonna lie to you guys. I haven't used this equation nearly ever. Okay, but it does become very useful when you need to find areas of sort of rando trigonometric shapes like this. Okay, and it's real easy to sort of figure out, right? So suppose we had a house on a corner lot. Find the area of the front yard, right? But the area of the front yard is this shape right here. Okay. Hopefully you guys see what this is. This we can call A, this we can call B, and this right here, this 135, that's going to be our angle C. I know this is not the best way to do it, okay, in terms of how the law of sine was written down. This, I think, I'm gonna sort of AB sine gamma. That's the better way to write it. That's the way I remember it. Okay. Okay. But at this point, it's just plug and chug, right? So it's going to be equal to 1/2 56 times 40 times sine of 135 degrees. Okay. Again, check your calculator, make sure that it is set to degrees. Okay. And if we throw this all in, right, 56 times 40 times sine of 135. Oh, come on. I am so glad that the semester is almost over. Times 791.95 feet squared, since this is talking about an area, right? Woo! We're getting there. We're getting there. Okay. The last thing I have for you guys to do is application problems. So this one's for everybody, okay? Uh, it looks difficult, but it really isn't, okay? I'm going to be using, we're going to be using the law of sines to figure this out. This is essentially um, the basis of, if you ever heard of triangulation of things, right? Technically, you just need two observations from two different locations and some known values from both locations, and you can automatically determine the location of a third point. Okay? Like I said, we will do this later during our quick check time. I believe after that is lecture questions. If you have any questions on the stuff that I just covered, I know it sounds complicated, ask during our quick check time, or come downstairs to the tutoring center. We'll cover it there. Okay? Besides that, happy studying.